So this is part 5 of writing a PIC Micro-controller game, and in this part I'm going to go through lighting the LEDs. So to start with, I'll just go through the top few lines of the code. So this top line, it just tells the compiler or the assembler what the actual PIC device you're going to be using is. And then here I include a load of definitions which are relevant to the PIC device that we're going to use. And this third line is configuration options. So this is configuring the configuration byte within the PIC microcontroller. And you do things like, here we're telling it we're going to use the internal oscillator. So if you're going to use the external oscillator, then you'd need to use a couple of pins to actually configure that. But as we want to use most of the pins, we're going to use the internal oscillator, and it also uses less hardware as well. And unless you need to use external oscillator, it's probably not worth it. I'm going to turn the Watchdog Timer off. We don't need that. Normally it's good to have that on, because if the program crashes or gets into some kind of hang state, then it will reset the device for you. And this is a delay on boot. It doesn't really matter whether you got this on or off. Put it on by default. Master clear is a pin. It defines one of the pins on the device as a master reset. And if you switch it off, then you can use that pin as an input. We're not using that as an input, but we're switch the master reset off. We don't have a reset button on this. And then there's a Brownout Detection, and this is just to do with if the power supply gets, if the PIC microcontroller detects there's power supply issues, then it can reset, and it can alert you that there was a problem with the power supply. We just turn that off because we're not going to do anything with that. And then code protection off and data protection off. So if once the device is written, if these are switched off, then you can read back the data which you've written to the device when you programmed it. So if you wanted to protect your code, you'd switch these on, and then no one could read your code. At the top I've got just like a open source license. This code is going to be open sourced, so the copy of the open source should go license should go with the code at all times. And then I just have a little header which says what the program is actually doing. So there's a few sections at the top of the code. One where define constants. So anything we want where we want a value, like this number 7, we want to refer to it in the program as something which is more human readable. So if I put 7 in the code, it wouldn't really make any sense. But if I put where I've put f underscore, that's like a flag, which is defines a bit in one of the words or one of the bytes. And I've got LED sequence pause, so when the sequence of the LEDs animating is paused. So I understand that a lot better when I come across it in the code. These GP5 and GP2 and GP0 and GP4s, they're all defined in this PIC header file. So these are all standard definitions of PIC microcontroller, which I'm redefining for me to define the switches and LEDs. For the 4 switch LEDs, so I can refer to them in code. It makes more sense than putting GP5 and GP4. And then I'm defining, although we're not covering the speaker in this particular part, I'm defining speaker because I'm using that definition in the initialization, so I put that in here as well. But apart from that, I'm just defining anything which is to do with LEDs, and also some flags which are needed for initialization. So after the constants, can come down to defining actually what goes in particular RAM bytes that you have to program with. So I use a couple as temporary working areas where I can just like put things temporarily as I'm going through a function. I probably use more than just 2 in the final application, but I'm using 2 in this example. Then I usually have an app flags in most of my programs. If it's nice to have little single bits of information you can store in one register, so you can use that single byte of RAM and save a lot of RAM just by using that for 8 different things. And for this demonstration, what I do is I store the actual state of the LEDs in the RAM register as well, rather than just referring to them in the GPI port, which you could do. it's nice to have a place where you can work on them, knowing that you're not affecting the GPIO port. And then when you actually want to write them out to the GPIO port, you can actually just take this register and write it out to the GPIO port as you need to. This sequence LED sequence address. So when I define some animations for the LEDs, so a series of ways the LEDs light up in succession, and when I want to play them back, I place the address of the animation I want to play back in this address register, and then this is a way of keeping track of which part of that animation I've actually got up to. But that will come clear later on in a function. And then define where the code starts there. At the very start, the address 0, this is where the PIC microcontroller resets to. So this is where your program always starts from. And you've got 4 bytes of memory which you can use before you get to address 004, which is where your interrupt handler is located. For the interrupt handler, because we're not handling interrupts at this point, but we'll do ultimately in the application. But right now, I just put a return from interrupt instruction. And it's nice to do that, because if you don't do that and somehow an interrupt gets triggered, even though you haven't, one shouldn't get triggered because we're not going to configure it. But just to protect ourselves, we'd put a return from interrupt, and then that should continue running the program. Whereas if you didn't do this, then it would have an undefined effect where it would go through your initialization code again and completely stop the operation of the program. So in this first 4 bytes, I have an instruction which I use to clear RAM values. So when you power up a PIC microcontroller, you get random values in the RAM addresses. And so what is nice to start from like a clean sheet of knowing exactly where you are. And just clear out all the RAM values. So here I'm putting the address of the first RAM value into the indirect addressing pointer, and then I'm putting the number of RAM bytes, which is 48 RAM bytes I want to clear. Now there is 64 bytes, and I'll come to it later on in a later part as to why I'm only clearing 48 bytes of the RAM. But for now, I just want to clear the first 48 bytes. And then because that's the first 3 bytes of memory, we could continue at this place called init, which is just down here. And this is where I call clear RAM. And I'll go through the function later on as how clear RAM function works. So this first part of the program is hardware initialization. So we've cleared the RAM, and there's 2 register banks. So I'll just go to the datasheet quickly. So in the datasheet for the PIC microcontroller, it shows you the register banks. So the one on the left here is register bank 0, and the one on the right is register bank 1. And you switch between them depending on which registers you want to use. So in here, at address 01 in register bank 0, you have a timer register. But if you just switch to register bank 1, then you have at 0 what you would refer to as 01. You have the option register, whereas the actual address is 81H, but that's you're adding the 8 on because the register bank is the bit that you set for here as bit 8. And so some registers are the same, so it doesn't matter. So for this PCL register, it doesn't matter which register bank you're in. You can access the PCL register, but otherwise you need to select which register bank you want for the registers you want to use. Now, the most used ones, they've put in register bank 0, so most of your time you spend in register bank 0. But for the lesser used registers, you switch to register bank 1, and then you only really need to be in there for a very short period of time. So for the indirect addressing, which we're using, there's this FSR, which is the address in RAM that you want to access. And then you access this indirect address register, which is called IDDR. And you can actually access the RAM locations from there, and that gives using indirect addressing is a big advantage because you can programmatically select with an offset where you want to reference in RAM. So earlier I was talking about initializing, clearing the RAM values, and that's in the register bank up at 20H. And on this particular microcontroller, whether you're in register bank 0 or register bank 1, you're still actually accessing the same registers, which are just these ones here. And you've got 64 bytes. And like I say, I only initializing the first 48 bytes in my program. So returning to the program, so after setting register bank 0, then continue with the hardware initialization. There's a comparator on the PIC microcontroller. We're not actually going to use that, so what we do is put it in the very lowest power mode that it can be in. Because it's a battery powered application that I'm doing, and I'm going to only be using like a coin cell battery, I want to reduce the power, and especially in standby mode I want to keep it as low power as possible. So that's what I'm going to do with register bank 0. So going back to register bank 1 now, and I'm going to initialize the GPIO ports for use with LEDs. So this TRISIO is defines what is an input pin and what is an output pin. So I'm clearing that value. So it's all going to be zeros. And the easy way to remember what's in and out is a 1 looks like an I, so it's an input, and a 0 looks like an O, so it's an output. So if I'm clearing them all to 0, it's going to all be outputs on those pins. So back to the register bank 0. I may have accidentally said 1 there and 0 there. But anyway, we're back in register bank 0 now. And what I'm going to do, so this is where I can use some of my definitions. I'm going to use a bit modifying operation. So what this means is rotate the bits to the left. So I'm saying I'm just going to have a bit in bit 1. I'm going to rotate it by the number of bits offset that LED 1 is. And then I'm going to OR that, which is effectively adding a separate bit. I'm going to use the same operation, but for bit 2, which is going to be a different offset. I'll go through some of these bit operations in separate videos. If you want to know how these operators work, I'm going to go into more detail in separate videos. But I'm just going to keep it a simple explanation of the program flow here. Then you can refer to other videos if you want to know more about the bit operations. So with all of the LEDs, I basically add them all to the W register. So there's only one working register in the PIC microcontroller, that's W register. And then going to move the W register into the GPIO port. So I'm switching all of the LEDs on, or at least I'm switching the values on. But actually, the way that because the LEDs are pulled up, it's actually turning them off. So it says outputs on, but actually it means turn the LEDs off. But that'll become clearer later on as well. Then so that's the hardware initialization done. So now I'll just do the software initialization. So I call a function in here called reset app, so which means I can reset the software. So I only have to initialize the hardware once, and then I can reset the software. And where I've got these comments test harness, so all of the code is going to be in the final application, apart from where this code which is surrounded with test harness, and this is just a simple bit of code which I'm using to demonstrate the functions for lighting the LEDs. But I'll skip over that at a minute. I'll come back to that in a second. So this is just the reset app, and this is a cut down version of what ultimately going to be the reset app, because it's only going to be referring to things which are related to the things I need for this demonstration. All I'm doing is resetting some flags in the application flags. So there's a flag which you can use to tell the software that you want to reset the app. I'm switching that off. So as I'm in the reset app function itself, I'm saying, okay, I've called that's been called, so I can reset that flag. And I'm also clearing the pause flag. So there's a flag which is used to pause the application, and that's being cleared as well. So it's making sure the application comes into it running. So I'll go through. This is the actual test harness. So this code itself won't be in the final software. But the calls to the functions will be, but in a different kind of context. But so this is just this is just the calls for actually doing this test right now. So First of all, I'm going to actually, even though I've just, in the reset app, I've uncleared the pause. I'm setting the pause because when you run an animation of LEDs, the application has to be in paused mode. So the animations happen when the application wants to show you something, but doesn't actually continue to do anything whilst it's showing you. So in order to show an animation, I get the address in Eeprom because I store the animation definitions, which I'll show you in just a second. I store them as part of Eeprom, and so I load the address that I want to use. So this is LED sequence rotate clockwise, and then I just call the function with the W register set to that address to set LED animation. So that sets the animation we want to use. So I'm just going to skip to the end of the program just quickly to show the Eeprom definitions. So here at address 2100, this is where the Eeprom definitions are stored. And I've got a series of animations which are to do with the LEDs animating. So this is the LED sequence rotate clockwise. I define it as a series of instructions. So LED 1's lit and LED 2's lit, then LED 3's lit, and then LED 4's lit. And this part here where I've got FF, that means the end of the sequence. And so once it gets to FF, the program knows that it needs to start the sequence back at the start again. So it will go back up to this first instruction, LED 1 again, and it will just keep going around in that loop. But I have a series of animations. So when setting levels, this says to only light LED 1, and this flag here, which is LED sequence pause, that means don't animate. So it'll only display this first thing and it won't animate further. So it's just that flag I put in there just to get around the animation, and I can define how to do this sequence stuff, because I can actually do an offset of the level number into this byte array of bytes as to which level we're on. And then I have this LED animation for win and LED animation for lose. So I also store some other stuff in the Eeprom, which we'll come across later on in different parts of the explanation. I ultimately use all the Eeprom area up. So if I go back up now, up to the test harness. So I've set in place that I want to animate the LEDs. And you only have to define that once. I'll go through these calls separately just after I've gone through what this test harness does. And then I call next animation sequence. So that steps it to the next element in the animation sequence. And then when it gets to the FF, it'll go back to the first animation sequence. So it'll just, as I'm in a loop here, so this loop defined here, and I go back to the loop so all the time. It will just keep going around that sequence as part of this demonstration. And then call LED display. So when I'm animating, when you call in this next animation, it doesn't actually update the display. It's only when you call this function LED display that it will actually update the display. And then I call the pause here, which is defined here. And because it's in the test harness, it's not the pause function which goes in ultimately in the application. I've actually got a pause function which I use in the application, but that's using interrupts and timers. Here I'm just doing a huge loop counting. So this first loop counts 255, and then this outer loop counts 255 of the 255. So I think that's 68,000 or something. So it counts 68,000 times just to put a delay in, so that when it animates, it's visible to the human eye rather than just animating so quick that you can't see the animation going. Just for the test, and that's all the demonstration is. It will animate the rotation of the LEDs in a clockwise direction. But now I'll actually come to the actual functions themselves. So I'll just go through them in order that they are here. So the LED display function just handles taking what's in the register LED state which are defined in the RAM registers up above, and placing that into the GPIO ports, but it doesn't actually yet place it into the GPIO port as you might normally expect. It doesn't put it on the GPIO port. It sets the input and output values on the input output definition TRISIO, and that uses that to switch on and off the LEDs. And the reason it does that is that when the output is high, the LED is switched off, but the output GPIO port is always on set to low. So all I have to do is set it to an output, the port to an output, and it will then set the output to low and turn the LED on, and then make it an input, which makes the when the GPIO port's an input, it's high impedance. There's no voltage and there's no ground on the pin, and that will then turn the LED off. And the reason for that is that when it's on the, as a high impedance, it's not taking any current in the pin, so it's actually a very low power way of using it. Normally, I would just use the GPIO pin as an input and output to light LEDs, but because this is using a coin cell, this slightly more complex method, which isn't as easy to understand as just using a GPIO pin as an output and setting it to high and low, but the gains that you get for saving power are fairly significant. So because when I set the value on the port to 0, it turns it on and the LED on, and when it's set to 1, it turns it off. So it's kind of reverse logic. So here I'm using exclusive OR in all ones with the value which is in the LED state register, and that has the effect of inverting those. So then it actually makes, if it's 0 in the LED state register, then it'll actually make it turn the LED off, and if it's 1 in the LED state register, make it turn it on. So it's just to make it more logical for the person that's reading the code to understand, in that outside of this function, what you do is you set the LED state to 1 to turn it on and 0 to turn it off. And then I just mask out the LED. I only want to change the LED pins, because I don't want to change the speaker pin, which is also an output, and I don't want to change any input pins either, which as a fact we don't have on this application. But if we were to define some additional actual functionality later, then this would mean that programming it this way means you don't interrupt that. So we only mask out the pins that we want to use, which are all the 4 LEDs. Then I need to go into bridge bank 1 in order to access the TRSIO register. So I set all the pins to as I want them, inputs or outputs, to light or unlight the LEDs. Go back to register bank 0, which is the default really, because that's where we most of the registers we want are used. And then this is a slight bit more sort of logic. So I'm doing the same as what I did up above to say I want just to select the LEDs here, but then this tilde sign, that inverts it. So I'm inverting the selection of the LEDs, and then I put that onto the actual GPIO port here. So I make sure that all the GPIO, the values are 0 for the GPIO pins. I could have done this in the initialization, but if I do it here, then I make sure that the outputs are the value I want them to be, in order for the LEDs to light as I want them. So the next function handles setting the LED animation, and it's a very simple one. So in the comments up above the function, you usually have what you have to call the function with, if you have to, and what the function returns if it returns anything. So in the W register, I pass in the address of the LED animation in Eeprom. So I clear the sequence count. So it's always going to start from the first LED animation sequence. Then I move what's in W register, which we passed into the LED sequence address. So it sets that. So that initializes how the animation starts. And I clear the LED state. So what I'm going to do is, if there's any LEDs that are currently lit, I'm going to switch them off, because I'm going to call LED display. So that switches any LEDs which are currently lit off, so that it will start the animation nice and cleanly from no little LEDs to how it should be in the sequence. And that's just setting the LED animation. So this is the function which moves on to the next stage of the animation sequence for LEDs. And first of all, it checks to see if the application is paused. If it's not paused, then it will actually go and do the animation. Move on to the next stage of the animation. If it is paused, then it will only do the next part of the animation if the sequence that we're currently on for the LED animation isn't flagged to be paused. So if the current sequence of the LED animation says pause, then we don't want to move on from that particular bit of the sequence. So that was where I showed earlier where it's set in the level, doing the level display. And so then, if it wants to go on to do the next part of the animation, it moves the the address of the animation that we're using into the W register. It then adds the offset that we're currently at. So this is the offset in the animation where we are. It adds that to the address. So now we've got the address in Eeprom where actually we want to get the next we want to get a definition of the value, but this increment flag moves it to the next one, which is the one we want next. And we call a function called read Eeprom, and all that does is it takes the W register, which we've just set up here with the address where we want to read, and it returns into the W register the actual value that was in that address. So the address that comes, the data that comes back is the actual data from that Eeprom address, and using exclusive OR again with FF. And this time, rather than inverting, we use it to do a comparison to see if the value is FF. Because if the value is FF, then it will set the 0 flag, and we can test that. So we're just testing here to see if the value that we've read back is FF. If it is, it means we need to go back round to the beginning of the animation again and get that first value. And we do that using recursion, which is quite a complex programming technique, but very efficient because it's very efficient at the code you're writing. So if it wasn't, it skips over if it was, and we wouldn't need to read again. But if it wasn't, then it just goes to this is the next value we use. And because we were doing a test using FF, using exclusive OR, I have to do that again to undo the exclusive OR I did up here for the comparison. And the reason I have to do that is because it's very limited to how many registers you've got. You've only got the W register to work with. So when you do a test up here, you then need to undo that test if what you found isn't the value that you were checking for. And I can then use what's in W register to update the LEDs. So slightly complicated there, but once the LED state, that is, that's not actually updating the GPIO port, so that's done in a separate call to a different function. But this is the register, which just holds what we want in the to display for the LEDs. So if I go back up to this comparison up here, if it was set to FF, then we get to this point here. So where we reset the offset count of the LED animation back to the beginning again, and I call the function that we're currently in. So that's the recursion. So from within the function, I'm calling the function itself. This time again to get the address now that we've cleared the LED offset count. So when I call the function now, we get the actual first animation sequence that we want to display. Now you have to be careful with recursion in PIC microcontrollers, because the first time I'm in this function, that's one stack level count. Now that I've called the function from within the function, we've moved on to another stack level count. You've only got 8 stack levels within the PIC microcontroller, so you can't do much recursion. But in this particular example, we can do, and that saves us having to write any extra code where we are here, just to get the first value again. So we can just call the same function, because it does what we want to do. Now when we come back out of there, because here I'm undoing the exclusive OR here, and we're about to run to that line of code, but we haven't, at this point, we haven't done an exclusive OR. So I actually have to do an exclusive OR there in order to set up a state where I undo the exclusive OR with the exclusive OR I did to undo the state of this exclusive OR up here. So it's quite a complex piece of code. If you read through it a few times, then I'm sure you'll get to see how it works. But it uses, this is one of the advantages of using assembly languages. You can do it once you know these tricks. You can do some very slick code, and you can put it in some very small amounts of memory. So if you're using a C compiler to do the same code on a PIC microcontroller, it wouldn't be as efficient for space, but you can actually save a lot of memory by using some of this code, these techniques here. And so we've gone back and we've read the first sequence, going through that method of going through the code, and set it into that value, which is the first sequence, into the LED state, ready to be displayed when we want to display it. Then we come out there. Again, I'll break some of those concepts out into separate videos to make them a bit simpler to understand, and I'll go through diagrammatically showing how that kind of stuff works, those principles work. And then finally, there's a couple of these small functions which get used in the ultimately. In fact, I use these in a lot of the applications I write. So there's a simple one to read Eeprom. So you're just using a call statement. So you set up a W register with the address you want to read. Sorry, there. And then when it returns, you get what you've read in the W register there. And that's all it does. So it goes into register bank 1 because that's where you need to be to set the Eeprom address. And you set that with what's in the W register. And then you have to set a bit on one of the registers in order to say to the microcontroller, I want to read Eeprom. And when that's done, you can just read straight from the Eeprom address into the W register. And then we set back to register bank 0 and return what was in the address in the W register. And so here's the clear RAM function, which I mentioned at the very beginning. And in this, I'll break out how indirect addressing works in a separate video because it's not easy to pick up the concept from just going through the code like this. But what it's doing is it's clearing what's in the address which we're currently pointed to with the indirect address registered address. So it's clearing the first RAM value, then it's incrementing the address we're pointing to, and then it's subtracting 1 from the W register, which the W register is the count of how many bytes we want to clear. And I'm using add-in FF as a bit of a trick again, because in binary counting, if you add a -1, which is what FF is, then you subtract 1. So you can easily decrement flags, decrement registers, but you can't easily decrement the W register. But this actually has the same effect. And I can check to see if the result of that decrement of the W register was 0. And if it wasn't, then I can go back round and clear the next address. So it goes back up here, clears what's in the RAM register, increments the address, decrements the count, and it keeps going around there until it's cleared all the RAM registers that you want to clear. So that's the end of the first code explanation demonstration. I'll go on to do explanation of the functions which I use for reading the switches and the keys. And I'll add that to this code. So as I slowly progress towards actually having a full set of code as the final application. So at the end you'll be able to upload that and write that to a PIC. So I've written the code to this PIC microcontroller. I just put it into the circuit, and you should see the LEDs animating. So that's what the code for demonstrating the LED code actually does.